Myself, Dr. Rajesh Prasad. Today I'm going to discuss a topic on advanced master method. And my previous recording was on master method. So today we'll be talking about advanced master method where and its limitation of master method and how we can solve these limitations. So this is outline of the work, outline of the presentation. Master method, quick recap, and limitation of master method, and then we'll talk about advanced master method. So as we know that master method is used to solve the recurrences of the form Tn is A T n by B plus Fn, right? So we have three cases of the master method and here A greater than or equal to 1 and B greater than 1 and Fn is any positive function on time. And this is like problem is divided into a part, each of size n by b, and Fn is time to combine the combine the solution. So this is how it is written. So Tn is A Tn by b. If recurrence is not in this form, master method will not be able to solve these recurrences and will have another method for solving the recurrences. So as we know that this has three common cases, right? So Tn, let me see, A T n by b plus Fn. This has three common cases. Old master method has three common cases, right? So case number one, it's talking about if Fn is big O of this. This means that Fn is actually less than n to the power log A base B. If this is the situation, then solution is given by theta n to the power log A base B. This is already being discussed in the last video. So second case is talking about if Fn is theta equality, then solution is given by Tn equal to theta n to the power log A base B and log n, where here this can be log n. And in case number 3, if Fn is omega, this means that Fn is greater than n to the power log A base B, as well as if as well as this also satisfy the regularity condition. And what is regularity condition? Fn by B is less than or equal to Cfn, where C is strictly less than 1. If this is the situation, then Tn will be given by theta Fn. So these are the master like cases of the master method. So let's have the limitation. So actually in the case number 1, if we are just comparing Fn n to the power log A base B, this is not the only comparison. We are also checking another condition that in addition to Fn less than n to the power log A base B, we have to check whether Fn is asymptotically smaller than this or not, right? So if Fn is asymptotically smaller than n to the power log A base B, this should be n to the less than n to the power epsilon, where epsilon is greater than 0. So this is actually this situation. This need to be checked together with this condition. So so Fn by this, if it is less than n to the power epsilon, then case 1 will be applicable. Otherwise, case 1 will not be applicable. So case 3, we are checking three conditions in case 3. Number 1, Fn greater than n to the power log A base B. This is condition number 1. Condition number 2 is Fn by B less than or equal to CFN, where C is strictly less than 1. This is regularity condition. Number 3, we are also going to check whether Fn is polynomially larger than n to the power log a base b or not. So if this is polynomially larger, if this condition is satisfied. So 3 conditions we need to check in master method, right? Number 1, this greater than this. Number 2 is this. Number 3, Fn less than n to the power log a base b. So that means if this is applicable, then only we are going to apply the case number 3. Otherwise, we'll say that master method is not applicable. Let's have one example of this limitation. See, let's have one example of this limitation. Yes. Suppose we are writing suppose this is the recurrence. Suppose this is the recurrence. Tn is 4t n by 2 plus n square log n. So see this here. If you just check n to the power log a base b, n to the power log a is 4, base b is 2. So this is actually n square, right? So if we see here Fn is n square log n base 2 and n to the power log a this. So it's like very easy to check that case 1 is not going to be applicable on this recurrence because this is not less than n to e square. Case 2 is also not applicable. Case 2 states that this should be equal to n square, right? So that means case 3 seems to be applicable. Case 3 seems to be applicable because this seems to be n square. This is greater than n square. Yes. But actually case 3 is also not applicable if you check the regularity condition. If you check the polynomially larger case. So you know it is not polynomially larger than this. N square log n divide by n square. So this cancel out. This is equal to log n. This is not greater than n to the power epsilon, because actually so log n cannot be greater than. So this means that case 3 is also not going to work. So what is solution? Solution in this case is that we can extend the case 2. So this is the extension of the case 2 actually. So case 2 was earlier if Fn is theta n to the power log a base b, then solution was given by Tn theta n to the power log a base b into log n base 2. This was the solution, right? So, but this can be further extended, like if Fn is theta n to the power log a base b and log kn, where Lg is base 2. So log kn, and this k is greater than or equal to 0. This can be greater than or equal to 0. If this is the situation, then Tn will be this value, and whatever k we are choosing, this will be incremented by k plus 1. For example, let's say this question. So if we take this question, Tn is 4t n by 2 plus n square log n, we have seen that case 3 was not applicable into this recurrence. So, and so n square log n base 2 is theta n square. So we can check that, this 2, 1. So that means here k equal to 1. Clear? So k equal to 1. So solution is very simple, that whatever k we are choosing, answer will be easy, that Tn will be theta n square, and if you are choosing k equal to 1, it will be k plus 1, 1 plus 1 n. So this is theta n square log n base 2, and this is square. So this is very easy solution. So this method is easy if we can extend the case 2 of the master method, right? So what about if case 1, case 2 and case 3 and even extension is not applicable, then how to solve it? Then we'll be going on the advanced master method. So this is the advanced master method, right? So this advanced master method will cover all the cases whatever is being discussed. So the master method applied to recurrence, we know that of this form only. Now Fn is going to be given in this form, theta n to the power k and then log pn, where p is any real number and k is any number greater than or equal to 0. So, right? So, here only we are changing this Fn. So there are 3 cases to this. Number 1 case, if a is greater than b to the power k. If this guy is greater than this, actually we are only comparing a and b to the power k. Then Tn is given by this answer, theta n to the power log a base b. On the other hand, if a and bk are same, a equal to b to the power k, then we are checking p. P greater than -1, this is the solution. N to the power log a base b log p plus 1n. If p equal to -1, then this is solution, which is very important case to note. And if p is less than -1, then Tn is, this is the solution, n to the power log a base b. On the other hand, if a is less than b to the power k, this, then consider if p greater than or equal to 0, then Tn is given by b, this, and if p less than 0, then Tn is given by this. So these are the cases of the advanced master method. So let's have this example. You see, this is like example of the binary search algorithm. Tn is Tn by 2 plus big O of 1. We can also solve this question by using the general master method, but let us apply the case of advanced master method. So you see here, Tn, A is here 1 and B is 2 and K is here 0. This K is here 0. This is the formula, and P is also 0. So now A is 1 and b to the power k is like b to the power k, b is like 0. So A equal to actually here, A and A equal to b to the power k, 1 equal to 2 to the power 1, 0. So this is actually 1 equal to 1. So that means this is the case number 2. Now P is 0, so 0 greater than -1, which is true actually. If 0 greater than -1, this is the case, then Tn is given by this answer. Tn is theta n to the power log a base b log 1 base 2 into log p plus 1 into n. So solution is theta n to the power 0 and p is 0, so 0 plus 1 n. So answer is given by theta log of n. This is the answer. So it is like binary search algorithm recurrence, and we can also solve this by the general method, is not a problem, but it is more convenient. Let's have another example in this series. See here, Tn is 2Tn by 2 plus big O of n. big O of n. So this we can write to Tn by 2 plus Cn, and here n Cn, so this can be written as like n to the power 1 log 0 n. So here is P is 0 and K is 1. This P is 0 and K is 1. A is 2, right? And B is 2. So now A is B to the power, A is 2 to the power 1, which is true. That means case number 2. Now P0, again this case is applicable. So solution is very easy, that Tn is theta n to the power log A base B is n into log P plus 1. So 0 plus 1 into n. So this becomes theta n log n, right? So actually this is Tn of solution of this recurrence. So it is very simple. Let's have another example. This example is also like easy. Case 2, still we are going to solve using case 2a. So it's like not a problem. Let's have another example. See here. Now A is 3, B is 2, right? And K is 2 and P is 0. So A is B to the power K is 4. A is less than B to the power K. That means we are going on case number 3. And here P greater than 0. So 3A. So solution is very easy, that in this case solution is theta n to the power K. K is here 2, right? And then log P 0 n. So solution is theta n square. So we are here in case number 3. Let's have another example. This example is like Tn of this. Now A is 3 and B is 2, right? And P is 1, P is 2 here, and K is 0, right? This is situation. Now we are comparing A and B to the power K. A is 3, B to the power K, like 3 here, and B is 2 and K is 0, right? So K is 0. So 3 is 3 here greater than 1. So that means you are here 3A. A is like A is 3 greater than 1. Then solution is straightforward. Tn is theta n to the power log A log 3 base 2, right? So this is easy solution. Yes. So let's have this type of recurrence, especially this extension, this advance is very popular, very helpful in solving this type of recurrence relation, where general master will fail. Tn is 2t n by 2 plus n divided by log n, right? So general master method case 1, case 2, case 3 will not work over here. So now here, if you understand it very well, so K is 1 and P is minus 1, because this can be written as 2t n by 2 plus n log n base 2 minus 1. So P is minus 1 here, right? And now A is 2 and B is also 2, right? So A is 2, B to the power K, 2 to the power K, K is 1. That means 2 equal to 2. Case 2 is applicable. We are going in case 2. Now, P greater than minus 1, no. this is not applicable. This case is not applicable. P equal to -1. Yes. So solution is given by Tn is theta n to the power log a base b is 1 into log of n, right? So solution in this situation is Tn is theta n log n. So this is one of the solution. Is important, very important. Many times this question has been asked in the examination. So okay, let's have another example of this question, this series. Suppose we have this question. Tn is 2t n by 2 plus n divided by log of cube n, right? So, and where base is 2. So definitely here a is 2, b is 2, and p here is -3, right? So p is -3 because this can be written as n log -3n, right? So p is -3 and right, and k here is still 1. So that means a equal to 2, b to the power k. Yes, this is correct. That means you are going in case number 2. But p greater than -1, no, this is not applicable. P equal to -1, no, it is not applicable. And see, p -3 is less than -1, correct, right? So that means answer will be Tn is theta n to the power log a. This is the solution. So this is very helpful to solve any kind of recurrences. So advanced master method will cover all the type of recurrences. This type of recurrences where you have Tn is a Tn by b plus this. So one more limitation of the master method, if you just understand it very well. So one more limitation of the master method. Suppose I am giving this kind of question. Tn by like say 2 plus 2 to the power n. So this kind of questions are not going to be solved by the master method. So it's not like polynomial. It is not fitting into this model. It is not fitting into this model. So that's why master method will not be applicable to this kind of recurrences. No, master method will not work, right? Yes. So, you know that our generation of the master method is coming from the recursion tree, because master method is also not going to work if recurrence is of this form. Tn is Tn -1, let's say plus n. So that means master method is not going to work over here when recurrence is of the form Tn minus. So it like then what is solution? So what solution of this type of recurrence is the recursion tree. Recursion tree. So recursion tree can solve this type of recurrence relations, right? So yes, let's see this. Yes. So how to solve this type of recurrence relation using recursion tree method? So you know, in recursion tree method, especially this type special recurrences, there are different kind of methods. So recurrences. So let's say root is like recursion tree over here. Then again Tn -1. We are sitting Tn here, we are placing Tn here, then n is here and Tn -1. Again, we can extend it Tn -1. Tn -1 is T n -2 plus n -1. So this is n -1 is sitting here. Then again Tn -2 will go here. So by doing this kind of thing, we ultimately reach to 1. Right? So So how to get the total cost? So cost of non-leaf node. So cost of non-leaf node is n plus n minus 1 plus n minus 2 up to 1, 2. It is like going to up to 2, right? And then 1. So we know that this is arithmetic progression, series from 2 to n. So we can sum it n minus 1 by 2. There are n minus 1 term. So Sn is n by 2 plus 2a plus n minus 1 into common difference. This is arithmetic progression sum. And this is in arithmetic progression. So we have n minus 1 term. So it will be n minus 1 by 2 and 2 times first term. First term is like here n and plus there are n minus 1 term. So n minus 1 into common difference. Common difference over here is minus 1. Right? So plus 1. So answer will be like if you just calculate it and approximate it to the big O of n square. So its solution will be big O of n square. So in general, there is shortcut for this type of recurrences. If Tn is Tn minus 1 plus n, whatever n you have over here, generally this is approximated as big O of n square. Just raise one power over here. So yes. Let's have like similarly, if you have another question, Tn is Tn minus 1 plus n square. This is also, so we are expecting its answer to be big O of n cube. Definitely its answer will be big O of n cube. So how to solve it? If you see here n square is sitting here, then n minus 1 square will be sitting here. See, because generally n square is coming, then n minus 1 here, right? And now Tn minus 1 will be Tn minus 2 plus n minus 1 whole square. So this is again Tn minus 2, right? So if we continue like this, ultimately we will get T1. So how to add them? If you can go and add them together, so answer will be total time Tn is n square plus n minus 1 square plus n minus 2 square, right? Up to and so on. It will go up to 2 and plus big O of n. Ultimately, we will reach to the leaf node. So class, this is actually n square plus, you can take n square outside the bracket. So it will be 1 minus 1 by n plus n square is going to be outside the bracket. It will be 1 minus 2 by n plus up to and so on plus 2 plus big O of 1. Right? So in this situation, we can take n square outside the bracket. So this will be 1 plus 1 minus 1 by n plus 1 minus 2 by n plus up to and so on plus 2 plus big O of n. So it's like very easy that if you take limit, right? Limit n tends to infinity. Why we take limit? Because we are interested in the upper time. We are interested in the upper time, right? So if you take n tends to infinity, so this guy will be 0, this guy will be 0, and this guy will be 0. So ultimately, total time will be approximated to n square 1 plus 1 plus and so on plus 1, right? So this like this is arithmetic sum, arithmetic progression, and this its cost will be n. So this is n square times n. So this is close to big O of n cube. So this kind of recurrence relation will be solved by this method, right? So Yeah, so many type of questions are coming like Tn is Tn minus 1 plus n to the power 4. So its answer will be totally approximated to Tn equal to theta n to the power 5. Right? So where master method is failing, you can use this recursion tree method. So thank you.